Hey, Jim, you know how water and oil don't really mix?
I've heard of that.
Well, we've talked about it a lot, so I hope you've heard that.
Oh, yeah, that's where I heard it. I heard it here.
This is where you heard it.
Right. Makes total sense. Yep.
So we're going to talk about today how sometimes water and oil can mix.
Okay.
And without a surfactant, there's another way.
Okay.
So we're going to talk about that. We're going to talk about some groundbreaking technology on how we can forever chemicals.
Okay.
And we're even going to talk about a new phase of matter we haven't really talked about, which is supercritical fluids.
Whoa.
Have you ever heard that word before?
No.
Okay, well, let's get into it.
I have been called supercritical before, but...
Oh, that was good. That was really good. I was not expecting that. I liked it. All right. Well, you ready?
Let's do it.
Let's go. Hey, I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast helps you understand the chemistry of your everyday life.
And today we have a very special dedication to Rachel R., our brand new Patreon supporter. Yay, we're so excited.
Yes, we are. Thank you so much for joining our super cool chem community of patrons. We love shouting out our patrons when they first join our Patreon. We were recording a few weeks early, and so we're just now getting a chance to actually thank Rachel, but we are so excited. Thank you for supporting the show and for joining our Patreon.
And I'm pretty sure Rachel is a chemistry teacher, so nice.
Nice.
And if you're interested in joining our Patreon, just so you know, we're thinking about changing things up, adding new bonus episodes or something like that are exclusive for our Patreon, so our supporters over there. So feel free to come on and check it out. We're really excited.
One of our big sticking points, though, is we don't want to put chemistry behind the paywall.
True.
So just so we're clear on that, you won't be missing on chemistry content if you don't join, but if you join, you'll get other stuff. We'll talk about our lives or things we think about or stories or who knows what, but we don't want it to be chemistry lessons. That's stays for free, stays on the podcast.
Yes.
But you get more behind the scenes, inside scoop. Who are these two people when they're not talking about chemistry?
Yeah. And that is really important to us from the very beginning. We have always said we want this chemistry content to be free. We want anyone who wants to listen to have access to someone who has an expertise in chemistry, no price. So that's really important.
Yep. Yeah.
All right. Well, thank you, Rachel. We're so excited to have you. And Rachel left a really nice review that we read and talked about on the Q&R from last week. So yay. And now are you ready to learn about PFAS part 4?
Man, part 4. So this is turning into like a real saga at this point.
It really is. But I think this is the last one, although we are hoping to do maybe a bonus episode surrounding all the questions we've gotten about PFAS.
Right.
So, but for this episode, if you're new here, if this is your first episode, welcome. We're so happy to have you. But we're knee deep in our series on PFAS. So probably you'd want to go back and listen or watch some of those past episodes in the last few weeks. We started out with just what they are. We talked about the history of them and how we got here. We talked about what individuals can do when possible. And now we're going to look at what chemists are doing. Okay, so sorry, got to find my place here because I went off script when I was talking about what we've done. Okay, so we know that you can remove PFAS from water in a relatively manageable way.
Right.
So, and we talked about that using granulated activated carbon. You remember that?
Yes, I do. Yes.
Last week. And the big reason that works is because water is polar and most of PFAS are not. They have like a polar head and a non-polar chain.
Right.
And so it works pretty well for most PFAS. But it's not perfect. Do you remember why it's not perfect?
Because depending on the PFAS, depending on the molecule, because there's so many different kinds, sometimes the size, because they have a polar part and a non-polar part, sometimes when the sizes of those parts are more equal, it's hard for whatever filtration substance we're using to actually catch it and keep it and want it to stay. It'll just go right through and not be effective enough to really like be worth pursuing.
That's true. And there's another reason that it's not perfect.
Oh, I know, because it doesn't destroy them. It just keeps them in a filter, so we aren't drinking them. Great. But they are still forever in that filter.
Yes.
Say you take the filter out of your fridge, throw it in the trash, goes to the landfill. All those chemicals, forever chemicals, molecules are just still there.
100%. That was so exciting. When you
Nice.
got it, I saw the light bulb go on. I was like, this is why I teach.
I was like, for a second, I was thinking like, man, I thought that was pretty much it. Like, I forgot about that crucial part until that moment when it light bulbed.
Yes. So that is what we're talking about today, is essentially we know that you can get rid of PFAS from water with filters. We talked about the carbon. There's also ion exchange and reverse osmosis. We're not going to talk about that because I think it's a whole other episode on the science behind those things, but those work pretty well. They're not 100% perfect, but yes, the problem is that then they still exist in the world. They're not gone. So currently, a method that's approved to get rid of them is incineration, but that's also not a great method because one, it takes a lot of energy, and two, it if you burn PFAS, if you don't do it perfectly, then it just changes them. It breaks them down into different PFAS. And also the people around the incinerator could just be breathing them in. And also, I didn't find this explicitly on a source. It just said vaguely that there were environmental concerns. But my concern is that then releasing fluorine radicals up into the air, which will mess with the ozone and cause a lot of other problems.
Yeah.
So I have concerns also about incineration. And it really is not.
And there's carbons too, right? So those would also release, which is the other thing we're trying to combat in other ways, is a bunch of carbon
just
in the
going.
atmosphere. Yeah.
Yes.
So, I mean, I guess it's not like that. In some ways it might be a drop in the bucket, but it's like, would it just change the problem to a different one?
I feel like it would just change the problem. And so we're going to talk about some other things that are happening. We're going to focus on one main one, which has a cool name. It's called the PFAS Annihilator.
Whoa.
And then we're also going to talk about some other ones that I think are interesting.
Dang. PFAS Annihilator.
I know. I feel like it's a pretty good name.
Yeah.
So, and we're going to go kind of in order of the ones that are like the best at this to the ones that are almost more just like ideas.
Okay.
And there's a lot that I'm not going to be able to cover. I just picked 3 of my favorite ones because otherwise this episode would be 100 years long. So first, a tiny mini chemistry lesson. I think we talked about this already, but what makes PFAS hard to break down is fluorine is really electronegative. We talked about that, I think, right? And electronegativity is essentially if 2 atoms are bonded together, the tendency to pull electrons towards itself in that bond. And so fluorine is the most electronegative atom. So if you're talking about bonds to carbon, which is what organic chemistry is all about, this is the strongest single bond in all of organic chemistry. It's the strongest bond between carbon and anything else is fluorine because it's pulling those electrons so tightly. It's also pulling the carbon in tightly to itself. So this is a really strong bond that can be hard to break, and that's part of their foreverness.
Got it.
You know? But now hold this in your mind, that it can be hard to break those bonds. So just even incineration may not be effective. So now we're doing something else. We're going into another reaction that's similar to burning, is an oxidation reaction, but it's oxidized by water, which is really weird because PFAS don't even really interact with water. So we're pivoting.
Okay.
And now hang that information that I just told you up on the shelf, put it in your shelf, and then now we're going to shift gears. Okay, what are the states of matter that we talk about?
Solid, liquid, gas, plasma.
We don't really talk about plasma.
We haven't. I feel like it's come up once or twice, maybe.
I feel like people have asked, but solid, liquid, gas, yes. I don't know much about plasma, honestly, but I do know about supercritical fluids.
Okay.
So we have solid, liquid, gas typically. And the way that I've oftentimes visualized this for you is the more energy you put into molecules from the solid state to the liquid state, if you put energy in, usually as heat, eventually the molecules or the atoms will move around more and more and more and more and more until it's not going to stay stuck together in this solid state anymore. It starts to be liquid.
Right.
So there's more energy for the molecules to move around more, and that's how we get to the liquid state. And then if you put even more energy in, they'll expand even further into this gaseous state.
Mm-hmm.
Now, what we don't talk about a lot of times is the relationship between temperature and pressure, but also if you're compressing molecules down, a lot of times that can affect the states of matter as well. So supercritical fluids have really, really hot molecules, super hot molecules that are moving around like gas. And then the weird thing that will happen is if you put a lot of pressure on them, so these gas molecules are trying to move around, and then you push it all close together, it doesn't really know how to act, and the properties will change.
Okay.
Because it's hot enough and has enough energy and movement to move around like a gas, but it doesn't have the space to do that. The molecules are closer together like water or liquid, I guess. So that weird boundary between gas and liquid at high pressure and high temperature is known as a supercritical fluid.
Interesting.
It's like if there's a boundary line between liquid and gas, it's playing right at that boundary line. Okay, so that's a supercritical fluid. One thing I thought about is like if you have a kid and you feed them a lot of food and so they have all this energy. As my nephew, it is wild. He can be tired and chill, and then you give him food and it's like you watch it burn into calories and like that he's moving around. He's like, I'm taking this energy and using it immediately. And like probably 15 minutes after he eats, he's like so much more energetic.
Yeah.
And so if you did that to him and then you held him tight, he'd be like wiggling around and trying to get free and be like, I don't know what you want me to do. That's kind of a good way to visualize what happens in supercritical fluid is like you give it all this energy and then tell it can't move.
Yeah.
You know?
Okay.
It's not going to act right. It's going to act out. It's going to act like a kid who's been given a lot of exciting food and given a lot of energy and then told they can't play.
Yeah.
That's essentially what's happening. Another way I visualized it is like if you had, you have a bicycle and you have a motorcycle and you have an e-bike just like flitting on that line. It doesn't act like a bicycle or like a motorcycle. It's like a weird hybrid.
Right. Okay.
So that's what supercritical fluids are. They're essentially not liquid and not gas. They're trying to be something in the middle of liquid and gas.
Okay.
And we can create supercritical water by putting it under really, really high temperature and pressure, higher than you could get like in your pressure cooker, really, really high. So we can have a super intense industrial type pressure cooker that is designed to turn water into a supercritical state. Okay. So the weird thing about it is if you put water in a supercritical state, all of its properties sort of start to change. And a big one that changes is it is now willing to interact with and dissolve nonpolar substances like oil and PFAS.
Oh.
Isn't that so weird?
That's really weird.
Yeah.
What the heck?
I know. Suddenly water is like, sure. It's like water and oil don't mix. In this case, they do.
Yeah.
Put it in the right conditions and it will.
Yeah.
High pressure, high temp, boom.
Interesting.
And there's not a lot of good information about why that would happen because it's such an intense environment that it's hard to study it at the molecular level.
Yeah.
So anyway, so we get this supercritical weird hybrid of water, supercritical water, and it will dissolve the PFAS. So that's exciting.
That's crazy.
It's crazy.
Would not have expected that at all.
Nope.
Like, one, obviously didn't know about supercritical water, but like, even if I did, I would not expect that would make a notable difference.
No.
You know? Weird.
Yeah, it's very weird. And so in that high pressure environment, oxygen atoms that are present in water that dissolve in supercritical water can react with a long PFAS chain, and it'll kind of, I'm hoping we can have Bri animate this for us or do some illustrations, but you'll have this long carbon fluorine chain, and It probably has that polar head on the end that could break off and form maybe into like an acid, depending on what is at the end of it there, like carbonic acid or sulfuric acid.
Mm-hmm.
But then the rest of the chain is just like carbons and fluorines, right?
Right.
And so that can react with oxygen to make CO2. Carbon reacts with the oxygen to make CO2, and you're also in water, so you have hydrogens available as well. So then you can have water lose its oxygens to the carbon, make CO2, hydrogen react with fluorine, and you get hydrofluoric acid, and you get carbon dioxide, and probably maybe also water.
Yeah.
So now you have broken that hard carbon fluorine bond up, and you've made carbon dioxide, which, you know, that's relatively harmless in terms of this reaction. But then on the other hand, you have hydrofluoric acid, which that would be really hard to deal with on a large scale because it is the most intense acid. I mean, like the thing that I always think of in hydrofluoric acid is the question that I get all the time. Have you seen Breaking Bad? Do you know where I'm going with this?
Yes.
Where am I going with this?
Dissolving bodies?
100%.
Yep.
100%. The number of times people are like, does hydrofluoric acid really dissolve bones? And I'm like, watch a different show. This is a small side pet peeve of mine, is that when you tell people that you're an organic chemist, the number 1 and 2 questions or statements you get is, can you make meth like in Breaking Bad? And
can you dissolve bodies like in Breaking Bad?
Well, they ask that, but usually it's, can you make meth? And then the other one is, I hate chemistry, or I've heard that class is really hard. Those are like my top 2 reactions.
Right.
And shortly right under can you make meth is, does hydrofluoric acid really dissolve bodies? And I'm like, I don't know. Why are you talking to me about this?
Yeah. And you're kind of like, I mean, I didn't get into chemistry to learn how to do either of those things. It wasn't what got me inspired. I wasn't like super into like, let's make meth or let's dissolve bodies or both.
No.
So sorry. I haven't tried.
I haven't tried. And also in chemistry, mixing things together and making new things is pretty easy, but the purification process is what's hard. We've talked about that on this podcast before. So like, sure, a lot of people could make meth if they can make it on the streets. Probably a trained chemist can also make meth. Rude. But also then can they purify it? Because if not, there's probably stuff in there that is not good to ingest. Not that meth is good, but
right.
Purification is really hard.
Right.
So don't take street drugs is what I'm saying.
Yeah.
Anyway, that's a side little rant. I was not planning to talk about that in this moment, but
yes.
There it went.
Maybe that's another thing we could have. We've been talking about some things we could do specifically for our patrons. We have a super cool community of patrons. Maybe a exclusive rants podcast.
Oh, yeah.
Here or there. You and I both have many rants that we could go on if we were allowed to. And some people might find those interesting.
They might.
So
honestly, it could be a whole different podcast that we do. It's just like, what are y'all? I could do 2 podcasts really easily, which is, what are you excited about right now? And what are you mad about right now?
Yeah.
I get those extremes. I'm definitely polar. Let's just say that. I'm a polar person. Just like those molecules, I have areas with electrons concentrated where I'm very negative and areas with no electrons where I'm very positive, and that is me. And that's Jam.
Yeah.
And both of our spouses are totally non-polar.
Yeah, very non-polar. Exactly. Yeah. That's right.
But weird that then we don't apply the laws of chemistry then to the fact that we married them, you know?
Right. That's a good point. That's where like the chemistry world and the relation world don't quite make sense.
Right.
You know?
The analogy
really
breaks down.
Yeah. In most cases with real life people, probably polar people don't get along. You know? That's a high chance.
That's
polar people
true.
will butt heads maybe, you know?
Unless you can get them polarized about the same thing.
Right. But non-polar people, I think, oftentimes do.
That's true. Non-polar people really do.
So.
Anyway. All right. Well, anyway, that was a huge aside. So
sorry.
That was a gift of our more relaxed atmosphere of our podcast these days.
Right.
So where was I? I was talking about hydrofluoric acid, and that's really bad. Yes. So how can you think of a way that you can deal with acid in the world? What
if you combine it with a base?
100%. And usually if you take an acid and a base and you mix them together, you get a salt, which is neutral, and water. So if you have sodium hydroxide and hydrofluoric acid and you react them, you would get, instead of NaCl, you'd get like NaF, you know? Or so you can just mix them together and get them in their not neutral states. They're in their neutral to humans. They're non-bad salty states in their ionic states.
Got it.
And you'd get water and you'd get carbon dioxide. So all those are pretty manageable outputs.
Okay.
So something that I read said, or something, it was actually an ACS video that I watched, said that if you use supercritical water to oxidize, react with oxygen, and break these things down, PFAS, it gets rid of 99% of PFAS in a minute.
Whoa. That's crazy. Wait, are they able to get the water to supercritical state that fast, or is it talking about once the water's already there?
I think once the water's already there.
Okay, I was thinking that seems like, especially at a large scale, it takes a while.
And I think it's expensive and it does consume a lot of energy to get water to this state. But there is a company named Battelle, I believe. Let me double check where I am in my notes here. So, since I'm looking at my notes, earlier this year, the EPA showed that supercritical water oxidation reduced PFAS total by more than 99% in a sample. And another article read that it gets rid of that much in 1 minute. A company called Battelle has used this technology to create what it calls the PFAS annihilator.
Nice.
And I think it has it housed in a stationary unit, but it also has mobile units. And I'm confused a little bit about if this technology exists and it works as well as it's working. And I read these articles last summer. Why have we not done more with this? Why haven't I heard more about like, okay, this is great and we're using it in all our water treatment plants, or we're having this company, we're paying them X amount of dollars to come clear our waterways? The only thing I could think is it's probably expensive.
Right. And doesn't seem to most people like a threat yet. Like we're still at that stage where we're trying to convince people.
It doesn't seem to us like a threat yet. I think companies and water treatment facilities and environmental biologists, they know.
Right.
We're the ones, the regular people like us are on the outs.
Or like municipal, say whatever your water treatment
municipalities, yeah.
It's like maybe the people at the treatment plant care, but can they get the money?
That's what I was going to say is I think it's expensive. So
if they can't convince the mayor or the whoever to do it, then
So I am thinking that right now, this is probably our best bet when it comes to neutralizing PFAS.
Okay.
It's technology that already exists. It's already being commercialized. And I'm guessing right now the biggest barrier is what you said is, do people think it's important enough that they're willing to pay for it?
Yeah.
Because I'm guessing it's energetically expensive and financially expensive.
Right.
So, but very exciting. And this isn't really super new technology, I don't think. I think it's just being sort of scaled up and being used in PFAS specifically. But I think it's been used to eliminate water contaminants before, because you can oxidize lots of things down to neutral products, down to like the individual atoms reacting with oxygen is usually your best bet. But you're not going to rely on this because it's so difficult to get supercritical water.
Right.
And that's why it's better, easier to typically just use incineration if you can. That's a much easier oxidation reaction. But that doesn't always work.
Right.
So I think that's why it's really coming to the forefront in PFAS technology.
Yeah.
There are a few other techniques, so I'm just going to tell you two other ones that I thought were interesting.
Okay.
One uses what's called ball milling. So it's literally using large balls to grind up solid PFAS contaminants. So like imagine soil that has PFAS in it, and you put it in with balls and they grind it all up.
What are they made of?
I don't know what they're made of. They require additives.
Okay.
I can't look at what they're made of.
Right.
But I'd have to go look it up real quick again.
But I was thinking what could do that well long term or whatever. Just thinking I don't know.
Yeah, so they use, let me see. I can pull the article up. It's metal balls. And they do it at high speeds. And what I thought was interesting about it is they create what's called solid state reaction. So literally what it sounds like, there's not a liquid medium for the electrons to move around or the atoms to move around in. They react in the solid state, and that breaks down the PFAS. But a lot of times to really make stuff happen, they have to add additives, and usually they use like potassium hydroxide, but that makes clumps and it can be corrosive, so that's not great.
Right.
So there are groups who are looking into other additives you can use. So it does work, but it seems like it's just not really the best, especially with these corrosive additives.
Got it.
So that's a way that works. But to make it better, they're working on using additives like boron nitride, which would be able to accept electrons and not have the corrosive clumping effects that potassium hydroxide has. So that's exciting. And then another one that I'm excited about is enzymes.
Okay.
We've talked about enzymes before with plastics. So I am excited about this, but this is like the least realized, I would say.
Okay.
So there's companies in the United States who are working to develop enzymes that can remove or break down PFAS in situ. So like I would think you'd be able to just put them into soil. You'd be able to put them into water and they would do their job. Hopefully they'd be safe. But there are already enzymes which remove chlorines have similar chemical properties to fluorine. So I think they're trying to work to engineer enzymes that would be able to break these down.
Got it.
So that's exciting.
Yeah, that's cool.
And there's a lot more. I mean, there's people who are like using electron beams. There's all kinds of stuff that you could look up. And we have articles that are linked that talk about other things people are doing. But these were 3 of my favorite. Yeah. And I was really excited about how effective it seems like the supercritical water one.
Yeah. It's cool because it feels like if these and more end up actually being able to be really worked out and further tested and employed in different ways, you're gonna need more than one. Yep. So we got to figure out what's the water one. Seems like it's already a done deal, but it's like, okay, well, what do you do with a lot of soil? Do you ball mill all the soil? Yeah. No, I mean you couldn't do that forever. You could do it for a certain section. Yeah. But you can't do that everywhere. And if PFAS,
do you ball mill all the activated carbon?
Right. Yeah. And so then it's like, okay, is there something like enzymes we can release in those situations where we can't take a substance from where it is and put it somewhere else? But like water systems, perfect. Yeah. But it just seems like we're going to need multiple options that all work in the different scenarios.
Yeah, right now there's not a great way to eliminate, like if there's PFAS in the soil, you just kind of have to wait until it gets into the water. And so that's what they were talking about is now we're looking at solid state, like solid PFAS contaminants. So
yeah. Dang.
Oh, that was really cool.
That's awesome.
Yeah. So that's some of the stuff that scientists are doing to, fix their mistake.
Or fix the mistakes of those before them.
Right.
Sort of.
Of our brethren, of the chemistry community.
Yes.
And the industry is also putting money into this as well. So
yeah.
I thought that was a fun little tidbit. And it also gives you 2 little mini chemistry lessons and builds on the non-polar polar water thing that we've talked about a lot.
Yes.
Water and oil.
100%.
So
super interesting.
Do you want to take a stab at explaining that? You can just talk about the supercritical water part. You don't have to explain all of the rest.
So supercritical water. Normally water being polar, when it's in its liquid state, would not want to react with something that's non-polar like oil. We've seen that a bunch. And that's an unfortunate situation we have with PFAS in that it is very hard for water to interact with it. Even though it does have a polar element to it, it has a non-polar part as well, which has meant, of course, water can't just break down PFAS. That would have been an easy solution forever ago.
I will say you said polar element and you mean like polar part, not literal element.
Sorry,
it's hard because it's colloquial versus periodic table.
A part of the molecule that is polar and a part that is non-polar. But somehow, someone figured out at some point this supercritical thing, which is still hard to wrap my head around, but that you can get water hot enough, but keep it from having the freedom it wants as a gas, that it becomes basically this superheated liquid that is behaving like not exactly a gas or liquid, but somewhere on that line there. And in those conditions, it starts to act different also in being able to interact with the nonpolar aspect of PFAS, where it can then break it down into, and taking the parts of it, it can become hydrofluoric acid. So the hydrogen and the fluorine can...
Hydrogen from the water, fluorine from the PFAS.
Can buddy up and become one thing there. And then the carbon from the PFAS and the oxygen from the water become CO2. And then you've got two different substances that you can deal with in a totally different way, which is CO2, like common every day. We are exhaling it all the time. Not great, but still better than PFAS.
Yep.
And then hydrofluoric acid, which wouldn't be great if we didn't have good options for how to deal with it, which is have it react with a base, right? Because acids really want electrons. They're like sort of starved of electrons, and bases have an abundance of them. You combine them, they do the reaction, fight it out, duke it out a little bit, and then they neutralize in a way where they create even safer end products like water and salts. And if we could do those steps, which they have done, which is expensive, then you've basically made the PFAS go bye-bye, and you've made a bunch of way more normal substances out of it.
Yes. Nailed it. The only thing I want to add as a clarification is this is an oxidation reaction.
Right.
And we've talked about a lot of oxidation reactions, but it's literally just putting more oxygen in and letting the oxygen react with other things. So like the oxygen reacts with the carbon to make carbon dioxide. Oxygen reacts with, well, I guess the hydrogen from the water reacts with the fluorine to make hydrofluoric acid. And also if you have the non-polar head or the polar head that can react with that and add oxygen and make it its own stable thing. So you're really just adding oxygen in. It's an oxidation reaction. And this is the same thing that happens when you burn a candle or when you let things rust.
Right.
And so we have episodes on that as well. If you want more about the nitty gritty about oxidation reactions, those are good, episodes to look at. Also, it's like you're kind of like burning the PFAS, but in supercritical water, which is so weird. Right.
And we have some great episodes about acids and bases too that are fascinating. And that one was a tough one for me to initially get, but
it's very confusing.
So fascinating.
Yeah. That might be one that I'd want to redo someday.
Right. Yeah.
I wonder if it'd be better nowadays.
It was hard. And I remember the way that chemists define acids and bases was so not the way that like me as a non-scientist does. But it took me so long to be like, wait, but I thought,
There's all these categories too. There's like different ways of assigning them. Yeah.
Yeah.
So that's it. That wraps up our PFAS series.
Wow.
How exciting, right?
Very exciting. And there's the most hope of any episode in this one. Like, these are some surefire ways to get rid of these things.
It's funny that you said surefire because fire extinguishers use PFAS, and I kind of want to do a series on what's in fire extinguishers.
That'd be interesting.
Because there's different types.
It'd be kind of like almost sort of like follow up on PFAS plus follow up on the fire alarms.
But I think I want to take a little break from PFAS before we do that one. But that's one that's like my brain.
Yeah.
So
cool.
We'll do a call back later. Nice that you said fire. Okay, great. Well, that's all for that lesson. I really, really enjoyed this series, and I appreciate those who asked about it and encouraged me to do it, including my friend Sarah. And in honor of Sarah, who asked me to do this series, I'm going to shout out today is National Voter Registration Day. So
nice.
If you're not registered to vote, please do it. It's free and it helps. And we want people like our listeners who care about topics like this to be the ones voting so that we can have people in positions of power who will enact real change regarding things like PFAS.
Yeah.
So
this is obviously coming out later, but you still have time to vote. So.
Oh yeah, this is not going to come out on National Voters Registration Day, which that'll give you a little hint that we recorded this on September 19th. I think it's today.
Yeah, it is.
So yeah, that'll give you a little hint of when we recorded this, but you can still register to vote no matter what day it is. So
yeah,
and it's free and it's important, and that is one of the biggest steps that we talked about of things you can do to really change PFAS in our environment is have people in positions of power who value things like that.
Yep.
So that's my happy thing for this week. What's yours, Jan?
Oh, that's your happy thing. I thought you were just gonna put.
I guess I could share other happy things. Oh, like
do you have another happy thing?
This is a good one. Is I saw some of our patron supporters who are also friends of mine in real life, Chris and Claire.
Oh, nice.
They invited us to come. They live in a town nearby ours, and we went and played bingo with them at like a local brewery type thing.
Nice.
And I've never played bingo as a grown up. It's fun.
Interesting. Yeah. I haven't played it in a long time either, so I can't even remember. I
mean, you're just trying to get 5 in a row, and they just call out like B. It's like BINGO at the top, and the B has 15 numbers associated with it, and I has 15 numbers. And so whoever gets 5 in a row first wins. So it takes no mental energy, really.
Right.
So it's a really good one to do while you're just chatting and having dinner with your friends. So it was really fun.
That is fun. I think that's part of it's chance, but also calling it first, right? So if somebody gets bingo at the same time as you have to say it first, right?
I think they honor if everybody gets it on that number. But you are supposed to yell it out loud. And if you didn't, people would say, silent bingo. Like the baseball chants. Sorry, I hit my mic doing that. And so it'd be like, silent bingo, clap, 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 clap. And make fun of you for not being loud in your bingo calling. There was a whole culture. It was they had I think it was 059 sounds like Sweet Caroline. So then they would sing bum, bum, bum after they would cheer. I was like, this is so coordinated.
That is really fun.
It was so fun. And it was just fun to get to chat and hang out. And the weather has been great in Texas. Fall is upon us.
Yes.
After the heat dome, it's 90 degrees feels amazing.
It really does. It's crazy. Because today's high is 95, but it's pretty overcast today. And it's going to drizzle just a little. But it's that doesn't feel near as bad as the 105 and straight up super hot sun that we were feeling. So
105 and even up to 109. And it was really, really, it's amazing how much better 90 degrees feels. So I think. Well, I was going to say, I was double checking to make sure it is national voter registration. That's what they told us about.
Yes.
So, yay, fun. So now that I've confirmed that,
let me think.
What's your fun stuff for this week?
I think the thing I will share is a somewhat small, mundane one. I bet later I'll be like, oh, I should have shared this. But we just had this weekend, we were able to take a bit of time to take the boys to the zoo.
That's so fun.
Which there's this little zoo kind of near us, it's really fun because it's just closer by. And, especially my older kid is really into animals and just loves it. And so that was just kind of a fun little deal we had to do. And the weather was great. So I was thinking about it because you said the weather thing. It was made it so much more enjoyable to be outside, taking your time, looking at animals and stuff like that. And that's all I had.
Awesome.
That's my thing.
Oh, I thought of another thing I want to share.
What?
This is just a quick fun shout out, but I went on another podcast.
Oh, yeah.
And it's not coming out until, I think it's November 4th, so you can look for it. But I went on a podcast called Ye Old Crime.
They record that far in advance.
I know. And I said November? And then I wrote it down, so let me make sure. But I was like, wow,
that's funny.
Amazing.
Yeah.
But I went on this other podcast, and she does this segment to have other podcast hosts on that's called Can You Crack the Cramp Word, which is a slang term in Old Victorian. And so she gave me slang words and I guessed them. I didn't get them right, but she also asked questions about chemistry and how the podcast started. And she was really nice. Her name's Lyn's on Ye Old Crime. So you can go check them out and support them. And you can maybe hear me in a little bit of a different context. Is not as formal as teaching a chemistry lesson. So it's really fun.
That's awesome.
So, November 4th. I double checked the date. Isn't that amazing?
Yes. That's crazy. Yeah, we feel like 2 weeks in advance is good.
Yeah, honestly.
That's when we're doing good.
And she's a mom and also has a full-time job. So maybe it wouldn't, I was going to say when you're a parent, you have to have your life together, but you're also a parent.
Yeah. And I do have to have my life together, but this sort of different parts of my life get the most together.
Get the togetherness. Yep. Yeah, definitely. Also, this is just kind of how Jem and I are.
Yeah. 100%. Yeah.
All right. Well, so thanks, Lyn, so much for having me on. That was really, really fun. And thanks for Sarah for telling me about National Voter Registration Day and for asking me to do this series on the podcast. Well, she asked for one episode. It made its whole own series all by itself. And thanks, Jam, and all of our listeners for listening and learning about PFAS. It's been really fun. Well, thank you for teaching us and doing all the mountains of research to do these episodes and to recognize that it could not be done in one, but needed 1, 2, 3, 4. So thanks for doing that. Melissa and I have a lot of ideas for topics of chemistry and everyday life, but we want to hear from you. If you have a question or idea, a thought you want to share with us, please do that on our website at chemforyourlife.com. That's chemforyourlife.com to share your thoughts and ideas. If you'd like to help us keep our show going and contribute to cover the cost of making it, we're just a little independent podcast, so it helps a ton. Go to patreon.com/chemforyourlife or tap the link in our show notes or in the description of the video to join our super cool community of patrons. If you're not able to do that, you can still help us by subscribing on your favorite podcast app, rating and writing a review on Apple Podcasts, and also subscribing on YouTube. That helps us to share chemistry with even more people. And subscribing on a YouTube is a good way to help us hopefully get monetized totally free to you. So if you want to help support the show for free, that is an amazing way to do that. This episode of Chemistry for Your Life was created by Melissa Collini and Jam Robinson. Jam Robinson is our producer, and this episode was made possible by our financial supporters on Patreon. It means so much to us that you all are willing to help make chemistry more accessible to more people. And just to shout out those supporters, they are Letila S, Bri M, Avishai B, Brian K, Chris and Claire S, Chelsea B, Derek L, Emerson W, Hunter R, Jacob T, Kristina G, Katrina H, Lyn S, Melissa P, Nichole C, Nelly S, Stephen B, Shadow, Suzanne P, Timothy P, and Venus R. Thank you again for everything you do to make Chemistry for Your Life happen. And an extra special thanks to Bri, who often creates illustrations to go along with episodes of Chemistry for Your Life. And you can see those over on our YouTube channel. You can thank Bri and support her by following her at intropic.artstation.com. And that first O in Entropic is a 0. And at McAllister Bri on Twitter. And if you'd like to learn more about today's chemistry lesson, you can check out the references for this episode in our show notes or in the description of the video. Yay, chemistry! Yay, chemistry!